Alright, this is a new topic from chapter 5, and in this topic we shall discuss about Earth's magnetism. Okay, so we have seen in the previous lecture video that if this is a uniform magnetic field, and if I place, let's say, a bar magnet with North Pole at this point and South Pole at this point, then this bar magnet will always experience a magnetic force. Okay, so which means this North Pole of the magnet will experience a force in this way, and the South Pole will experience a force in this way. So these two equal and opposite forces acting at at the two ends of the dipole, they will constitute a torque, which means this dipole here will try to rotate till it become parallel to the magnetic field B. Okay, so when this dipole becomes parallel to the magnetic field, then we see this position is the equilibrium position. Okay, all right. So similarly, we will apply this concept to study about the Earth's magnetism. Okay, so for this Earth magnetism, I think you might have seen, right, when you place a magnetic needle. Okay, suppose this is a magnetic needle, and I place this magnetic needle, let's say, on the surface of the Earth. Let's say this is a point A, and you will find that this magnetic needle will align itself, in this direction. That means the North Pole will be facing towards that side and the South Pole this side. Okay. Similarly, if you place the magnetic needle, let's say, at this point B, then you will find this magnetic needle, it is aligned in this direction, in which the North Pole is going this way and the South Pole like this. Similarly, if this same magnetic needle is placed at a different place on the surface of the Earth, then you will find this magnetic needle, it is aligned itself in this direction. Okay, so this different alignment of the magnetic needle in different direction at different places, it suggests that there is a magnetic field on the surface of the Earth, because a magnetic needle, it is like a bar magnet only, which when placed in a magnetic field, then it will try to align parallel to the magnetic field, which means the North Pole of the needle will always be in the same as the directions of the magnetic field. So it is seen here that at these different points A, B, C, the magnetic needle, right, are aligned themselves in different direction. So we see that the North Poles, right, this North Pole at this point A, it is pointing in this direction. At this point B, it is pointing in this direction. At this point C, it is going down. So that the directions of the North Pole of the magnetic needle always, it gives the directions of the magnetic field. Okay, so this is clearly seen, right? It is clearly understood that this Earth, right, it is like a magnet only, in which there is a magnetic field around the, right, the surface of the Earth. So because of the presence of that magnetic field, that is why the magnetic needle at different places on the surface of the Earth, it aligns in different direction. Okay, all right. So the question now is, what is the source of the magnetic fields of the Earth? Who produced the magnetic fields of the Earth? All right. Okay. So for that, we will look at this figure, in which this is the Earth, and let's say this is the axis of rotations of the Earth. Okay. Suppose this point is the, the geographic north of the Earth, and this point is the geographic south of the Earth. All right. Okay. Now, if the Earth, if the magnetic needle when placed on the surface of the earth, gets deflected or it gets arranged itself in the directions of the magnetic field, then who is actually produce the magnetic field of the earth? So here we will imagine that there is a magnet, there is a bar magnet which is lying at the center of the earth. Okay, and let's say this is the north pole of the magnet and this is the south pole of the magnet. So it is this bar magnet which is present right at the center of the earth produce the magnetic field of the earth. Now, as you know, the magnetic field lines are always produced from the north pole of the magnet, and these field lines, right, they will go from the north pole and they will enter the south pole. So these are the magnetic field lines which is produced by the magnet of the earth. Okay, then now again let me come back to the magnetic needle. If this is my magnetic needle, right, in which this end is the north pole and this end is the south pole. So if I place the magnetic needle, let's say at on the surface of the earth, and it happens that the north pole of the needle, okay, let's say it points this side, and the south pole it comes this side. Okay, so why it is so? Why this north pole of the needle it is going that side? Because of the south pole of the magnet of the earth. Because as you know, south pole always attract north pole. So that is why when you place a magnetic needle on the surface of the earth, like in my case, then the north pole of the needle will point that side and the south pole will come this side. So this is because of the attractions of the unlike poles. Okay, the south pole of the magnet will attract the north pole of the needle, and the north pole of the magnet will attract the south pole of the needle. So that is why if I say, right, if I want to determine about the north pole and the south pole of the earth, then I use this magnetic needle and I place it on any surface of the earth, then I will know where is the north pole and where is the south pole. Like in this case, the north-south direction is in this way, which means the north pole it is here and the south pole is here. Okay, so this north pole and south pole, right, it is known as the magnetic north pole and the magnetic south pole. So this magnetic north pole and magnetic south pole, which is actually determined by the magnetic needle, it is not the real poles of the earth. Okay, the real poles of the earth, it is actually NG and SG, which is the geographic north and geographic south. So the geographic north is here, but if you determine the directions of the north and south pole using a needle, you get the north it is here. Similarly, the south is here. Okay, so these magnetic north pole and the magnetic south pole of the magnetic needle does not tell you exactly about the directions of the north pole and south pole of the earth. Okay, so that is why I can see here that this magnetic needle, sorry, this bar magnet which is actually present inside the earth, it is making an angle 20 degree with respect to this axis of rotations of the earth. Okay, so please remember here that when you use a magnetic needle to find out the directions of the north pole and south pole of the earth, you are actually finding the the not the real poles but the the poles which is closer to the real poles. All right, okay. Now, so let us go further. In this figure, we have once again this is a line, and this line it is the axis of rotations of the earth. So this line it is passing through the geographic north and the geographic south of the earth. So this line, it is sometimes known as the geographic axis. So what is the geographic axis? A line which is passing through the geographic north and the geographic south of the earth is known as the geographic axis. Okay. Another point is, if I draw a line, okay, which is passing through the magnetic north and the magnetic south of the earth. If I draw this line, then this line here is known as the magnetic axis. So what is a magnetic axis? A line which is passing through the magnetic north and magnetic south of the earth is known as the magnetic axis. Okay. Now, we also have another line here, this line. So this line, it is known as the equator. So what is an equator? It is a line which is passing through the center, right, perpendicularly to the geographic axis, and it passes through the center of the earth. So this line is known as the equator. Okay. Now, if you want to determine the magnetic field at any point on the surface of the earth, then you require three parameters to know, right, completely about the magnetic field at any point. And these three parameters, they are known as the elements of the earth. Okay. So let us see what are these elements of the earth. Okay. The first is the angle of declination. And this angle of declination is denoted by the symbol alpha. Okay, so what is angle of declination? Alright, so before we define angle of declination, right, let me just give you, right, a brief idea about the planes, okay, which are passing through these axes. Okay, now look at this geographic axis. If I draw a plane perpendicularly, which is passing through this geographic axis, then that plane is known as the geographic meridian. Okay, and if I draw a plane passing through the magnetic axis like this, then that plane is known as the magnetic meridian. Okay, so it means if this is my magnetic meridian, and I have another plane like this, which is the geographic meridian. So these are the two planes, okay, passing through the two axes of the earth. Alright, so the angle of declination here, it means it is the angle between the magnetic meridian and the geographic meridian. So this angle between these two planes, right, it is denoted by alpha. And this is known as angle of declination. So that is the first element of the earth. Okay. The second element of the earth is angle of dip. So what is this angle of dip mean? Alright. So we have seen, right, that the earth behave like, like a magnet only, and it produces a magnetic field, okay, around itself. So these are the magnetic field lines which are going, right? These are the magnetic field lines which are surrounding the earth in this way. Alright. So at any point, let's say at this point, right, this is the directions of the magnetic field B. Okay. Or if you say at this point, okay, let's say at this point, this is the directions of the magnetic field B. Now, if you consider this point here, then you have this magnetic field B, it is acting along this direction. Okay, And this magnetic field B, it should be acting along the magnetic meridian. Alright. Now because this magnetic field, it is acting right at an inclined way, so therefore I need to resolve this magnetic field into two rectangular components. So if I name this angle as delta, then I will have the horizontal component as BH, and the vertical component of this B, it will be BV. So these two components, BH and BV, are the rectangular components of the total magnetic field at any point on the magnetic meridian. Okay, so now come to the angle of dip. It is this angle. It means the angles between the total Earth's magnetic field and the horizontal components of Earth's magnetic field. So that angle is known as angle of dip. Okay, all right. Now the third element of Earth's magnetic field, of Earth's magnetism, it is the horizontal Earth's magnetic field. So for the horizontal Earth's magnetic field, we denote by BH. So what is this horizontal components of Earth's magnetic field? So it is the component along the horizontal, okay, which is acting in the magnetic meridian. So that is known as the horizontal Earth's magnetic field. So by knowing all these three elements of the Earth, then you can determine the magnetic field of the Earth at any point, right, on its surface. Okay. So looking at this figure, okay, I can say that this BH, the horizontal components of Earth's magnetic field, it is equals to B cos delta, and BV is equals to B sine delta. Alright, so if you square and add these two, then you will get B square cos square delta plus B square sine square delta. Or I can say BH square plus BV square is equals to, taking common B square from here, you will get inside cos square delta plus sine square delta. Or BH square plus BV square is equals to just B square. Why? Because this cos square delta plus sine square delta is equals to 1. So 1 times B square will be B square. Okay. Or you can also say that this B, the total magnetic fields of the Earth at any point on its surface, can be written as square root over BH square plus BV square. So this is the equation to find out the total magnetic field at any point on the surface of the Earth if you know BH and BV, that means the horizontal component and the vertical component. Alright. Now let us see at some special cases here. Special cases. So my first special cases is at the equator. So at the equator mean along this region, right? Along this line. So along this line, what happened is this delta is equals to 0 degree. Okay. So how much is delta? 0 degree. So when because delta, look here, because delta right along this line, it would mean this delta, this angle delta is 0. So when delta is 0, then how much is the total magnetic field along that equator? So the total magnetic field B, using this equation, alright, okay, you get root over, okay, first I'll do it this. Let us find out BH. How much is the horizontal component? It is B cos delta. But at the equator, delta is 0 degree. So cos 0 is 1, so 1 times b will be b. Similarly, at the equator, your bv will becomes how much? B sine delta, but delta is equals to 0 degree. So sine 0 is 1, so 1 times b will be just b. Will be sine 0 is 0, 0 times b will be 0. So it means that at the equator, okay, the total Earth's magnetic field, it is just the horizontal component. Or I can say that right at the equator we don't have such vertical and horizontal component. We have, because this magnetic field, it is acting horizontally in this way. So it means that total magnetic field, it is equals to BH only. That means B cos delta. Okay, right. So this is the first case. And the second case is at the poles. So when I say at the poles, it means at these 2 points, right? So if you consider this line, okay, then at this pole, how much is this angle of dip? So when I say at the pole, then this B here, right, this B, it should be going down in this way, perpendicularly in this way. It should be pointing downward. So it means this angle delta will be 90 degree. So when angle delta is 90 degree, then my BH will be equals to how much? B cos 90 degree. But you know cos 90 is 0, so 0 times B will be 0. And BV is equals to B sine 90 degree. You know sine 90 is 1, so 1 times B will be B. So hence, at the poles, okay, we have seen here that the total Earth's magnetic field, it is equals to the vertical components of the Earth's magnetic field. So these are the 2 special cases about the Earth's magnetic field.